Hello everyone, welcome to the next lecture of MOSFETs. This is the last lecture in the series of MOSFETs. We are covering the topics on MOS amplifiers from chapter number 7 of Cedar Smith. In this kind of a final lecture, I am going to focus on doing some of the examples, and I hope that will help clear up more concepts for all of you. And starting next week, we will move to chapter number 5, bipolar junction transistors. And then we will come back to chapter number 7 and cover the contents of the amplifiers that are related to the bipolar junction transistors. Okay, this is the final lecture on MOS FET amplifiers, and we're going to do some of the examples. All right, so let's do this first example. So consider this circuit. You have seen this circuit before, in which our NMOS is being used as an amplifier. We connect a drain resistance RD here. You've seen this circuit much earlier in this chapter, right? So in this MOS amplifier, our supply voltage is 5 volts. Process transconductance parameter, MOS FET transconductance parameter is Kn. We want our amplifier to have an endpoint of this VTC. VTCs, if you remember, was voltage transfer characteristics, and we want to operate it at a point B. At point B, our value of the voltage, drain to source voltage, that is given is 0.5 volts. So the question is, what is the value of the RD that is required to operate this transistor as an amplifier at a point B? So let's go back to the voltage transfer characteristics quickly. Where is it? Okay, there you go. Right, so this is coming from this circuit, the same circuit that we are just discussing now. And what we want to do is we want to operate our transistor over here at a point B. If you remember, this point B is the edge of saturation, right? This is this edge of saturation point. And we know that at the edge of saturation, our drain to source voltage is equals to the overdrive voltage. So this is the point B. So our drain to source voltage at point B is equal to the overdrive voltage at point B, which is the value that is given in the question. Okay, so let's go back over here. All right, so we know that over here our drain to source voltage that is given at a point B will be equal to the overdrive voltage that is given at a point B, which will be equals to 0.5 volts. Okay, so we are interested in finding out the value of RD. So just by looking at the circuit, I know that my RD can be found out by VDD minus VDS over ID. Since we are talking about a point B, so we can say that this is a value at point B. This is also a value at point B. So we know this value, we know this value. Let's find out this value. So the second thing that we need to find is the drain current at a point B. We know that at a point B it is the edge of saturation, so it should be the start of the saturation region, half. So it will be half Kn VOV whole square. Again, VOV at point B whole square. You can also write the same equation as half Kn VDS at point B whole square. Since this value is the same as this value, okay? So if we will put down these values, half, our Kn value is 5, and our overdrive voltage is 0.5 square. If you are going to calculate all of these, your answer that is going to come out to be 0.625 milliamperes. Okay, so using this value, we can easily put down this value to get the answer. So our RD value that is going to come out to be now is 5 volts minus VDS at point B, which is 0.5 volts, okay, divided by the drain current at point B, 0.625. The answer that is going to come out to be 7.2 kilo ohms once you're going to solve it. Okay, so we ended up finding the value of the RD that is required to operate this transistor at point B on the voltage transfer characteristics. So second part of the question is, if the transistor is replaced with another one having twice the value of the transconductance parameter Kn, what new value of the Rd is needed, right? So the question is, if we are going to have a new value of a Kn, which is twice this value, right? So what is going to happen, right? So if we have a twice the value of the Kn, since this is a linear relationship with the drain current, so if my Kn will double, this will translate to doubling of the drain current as well. So if the drain current will double, right, if our drain current will double, if this amount will double over here, the resistance value that is required will reduce to half, right? So the value of the so the new value of the ID at point B new will be 2 times 0.625 milliamperes, right? So the new value of RD new for a new transistor, it will be 5 minus 0.5 over 2 times 0.625. So essentially your resistance will now half. It is the same value. So it will be 1.2 into 7.2 kilo ohms. So the answer that is going to come out to be 3.6 kilo ohms. Okay. Right, so it was a very simple question in which we want to operate a transistor at the edge of the saturation, which was point B on the voltage transfer characteristics. And we know that the value of the current is, this is our regular saturation current equation that we use. We know that at the edge of the saturation, our overdrive voltage and the drain to source voltage are exactly equal. So just having these basic concepts can solve this problem very easily. Okay, so let's move to our second question now. Okay, so let's move to our second question. Okay, so let's see the circuit over here. Now we have another circuit over here in which we have a transistor with threshold voltage of 0.4, the drain resistance of 10 kilo ohms, the Kn transconductance parameter of 5 milliampere volt square. Gate to source is this, supply voltage is this. Okay. As you notice over here is that, again, this is an overall circuit in which our VGS is composed of the biasing voltage and the time varying voltage. Similarly, our drain current will also be composed of the DC drain current and the time varying. Our VDS will be composed of the DC value and the time varying value. Okay. So the first part of the question is we need to find the values, these DC values, right? And we know that while finding the DC values, we ignore the AC quantities, or we can say that our time varying quantities are 0. Okay, so when I say that, so let's find in the A part, let's find the values of, let's find out these DC values. Okay, so let's solve this A thing, ID. Since we are operating this transistor as an amplifier, FET amplifier, so the drain current equation is half Kn VOV whole square. Again, VOV is half Kn VGS minus VT whole square. So half Kn is 5, VGS is 0.6, threshold voltage is 0.4 whole square, half 5.2 whole square. So if you're going to solve this equation, you're going to get, so this 2.5, if you will solve this, you will get 0.1 milliamperes. Okay, great. So we ended up finding the value of ID, and once we find the value of the ID, again we are trying to find also the DC value of drain to source voltage. Okay, so the drain to source voltage can easily be found by VDS is equals to VDD minus capital IDRD, right? Just using this circuit. Okay, so VDD is, we know that what it is. VDD, sorry, where did it go? Okay, VDD is 1.8 volts minus ID is 0.1 milliamperes into RD is 10 kilo ohms, right? Always make sure that all the units will make sense, right? So our drain current is in milliamperes, and then our resistance is in 10 kilo ohms. So that's why I just ended up writing like this. those a million kilo are going to cancel out. So make sure that you will take all of these things into consideration. Okay, so our value of the voltage that is going to come out to be, after solving this, it will be 0.8 volts. Okay, so we ended up solving the first part of this question, in which we find the DC values of the drain current and the drain to source voltage. Okay, so let's do the second part now. In the second part, we are interested in finding the value of the GM, MOSFET transconductance parameter, at the bias point. If you remember one of the earlier lectures, we ended up finding out the value of the transconductance parameter, which was KNVOV, right? So you can also try to remember, yeah, probably remembering is not needed. You can always have this formula sheets for the final exam, whether live or remote. So anyways, so this is the value, this is the equation that we ended up finding out, or the relationship we ended up finding out for the MOS FET transconductance parameter. It was directly proportional to the value of the Kn and the overdrive voltage. So if we have to find out this value, we know that the value of the Kn is again 5, overdrive voltage is VDS minus VT, 0.6 minus 0.4, so it is 0.2. So we ended up finding 1 milliamperes per volt. All right. So the third thing that we want to find out is the value of the voltage gain. So the value of the voltage gain, again, we ended up finding out it was equals to minus dm into RD. Okay, we can also go back and see where did we ended up finding out these values, right? For example, over here. So when we were visiting this voltage gain in more detail, right? So we started that lecture with that. Okay, so this was our circuit. We have we have the DC quantities, time varying quantities. We ended up solving all of these equations earlier in that lecture, and then we ended up finding out the value of the GM, which is KNVOV. That I've shown you earlier, and we also finding out the value of the voltage gain, which is minus GM into RD. Okay, so let's go back and solve that example where we are at. Okay, so our voltage gain now is minus GM into RD. So I already know the value of GM from my earlier equation from the part B, which is plus 1. So minus 1 into RD, the value of the RD is given as 10 kilo ohms. So the value that I got will be minus 10 volts by volts, right? Okay. The GM value was also 1 milli, right? So this milli and K can be cancelled out, and the total value you are going to get is minus 10 volts by volts, right? So you are getting an amplification of the 10 times amplification in your using this amplifier circuit. Okay, so let's do the part B. Now part B is interesting. All of the above three parts and most of the analysis here assumes that the channel length modulation effect was 0. Otherwise, this equation we should have used this parameter as well, right? But earlier we just assumed that the lambda was 0 and the channel length modulation was 0. Since there was no channel length modulation, so we ended up calculating the values in A, B, and C. Okay, so in the part B, now that part B states that we have a channel length modulation effect, and the lambda value for the channel length modulation effect is 0.1 per volt inverse. Right, so for the part D, our lambda value is what was the lambda value? 0.1 volt inverse, 0.1 volt, right? Okay, and so what do we need to find out? We need to find out the value of R naught at the bias point and the voltage gain, right? So what we need to find out, R naught at bias point and the value of the voltage gain, the value of the new voltage gain now, considering the lambda value or the channel and modulation effect as well. Okay, now again going back, if you remember when we were drawing these equivalent circuits in this figure, right? So we started with this, we said that our output resistance is infinite because in the saturation region our current does not increase, there is no channel and modulation effect, resistance was infinite, slope was 0. right? But what actually happens beyond the pinch off region, beyond this VOV voltage, our the length of the channel reduces and we get some finite resistance R naught, and that resistance will appear in parallel to the resistance, to the drain resistance. Another thing that we did earlier, so this was coming again from the chapter number 5, that the value of the R naught is proportional to the early voltage and to the drain current. And we also saw earlier that if we have to find the voltage gain, then essentially what just happens is, rather than having a voltage gain which was initially minus Gm into Rd, ignoring the lambda effect and the finite output resistance, with the consideration of the finite output resistance, that resistance will appear in parallel to the Rd. So we're going to use this two equations to find out to solve that lost part. Okay, now we have a lambda value, we need to find R naught and calculate the voltage gain, right? So we just discussed that our value of our R naught is equals to will be equals to VA over lambda. Sorry, VA over ID. Okay, so our early voltage, and we know that our VA is proportional to 1 over lambda, right? So if it is equals to 0.1, our VA will be 10 volts. So we have 10 volts here, and what is our value of the drain current? Our drain current was 0.1 milliamperes. So it is 0.1 milliamperes. So the value of the R naught that we will get is, it will be 100 kilo ohms, right? So this can be 10 to the 3 here, and 0.1 can go over here to make it 100. So the value of this finite output resistance is 100 kilo ohms. So let's find out the new value of the voltage gain. So the new value of the voltage gain will be minus Gm Rd in parallel with R naught, right? So all we need to do, let's look at the value of the Gm. Gm is 1, right? So we have 1 here, and then we have Rd. The value of the Rd is 10k, right? So we have 10k in parallel with 100k, right? So if you will just solve this out, the value that you're gonna get is minus 9.1 volts per volts. Okay, so bottom line is, you can easily solve this problem, right? So the bottom line that we kind of considered over here is, if you have to find the DC, so the first part important, right? If I will give you a summary of this problem, if you have to find the DC quantities, you can ignore the AC quantities, right? So this VGS or this VDS or this ID. So right now we are trying, in the first part, we try to find out the bias quantities, right? And for the FET amplifier, we know the drain current equation was half K and VOV whole square. We ended up putting the values and find out the current. The value of the GM can easily be found out by K and VOV. The value of the voltage gain by this minus GM into RD. And when we consider the channel length modulation effect, all you need to do is to consider that the resistance R naught will appear in parallel, that resistance R naught, which was proportional to the early voltage over the drain current. Since it's an NMOS, so it's a positive early voltage. For a PMOS, it would have been negative, so we would have taken a modulus value there. Again, for the R naught will appear in parallel to the RD, so your so essentially your new gain equation would just have, is just gonna have this parallel resistance there. So this is what we did in the last part, and solve this problem. Okay, so we have still a few problems left to do. Okay, so our next problem now. So let's consider we have this amplifier with an input resistance of 100 kilo ohms. Its open voltage gain is AV naught. So this is the third example we are doing. And then it has an output resistance, it has a signal source resistance and a load resistance, and we have to find the overall voltage gain, right? So if you remember the last lecture when we were characterizing the basic amplifier, right, our circuit should look something like this, right? It has a signal resistance, input resistance, output resistance, load resistance, right? And this was an open loop voltage gain, right? So we can draw a similar circuit and then solve this out. So when we solve the circuit, we also calculated all of these, find out all of these values. We find out the values of the voltage gain of the amplifier. We also find the value of the voltage gain or the overall voltage gain. Okay, so let's do the similar thing. Is this this now? Okay. So let's start with, I think I can start with making a circuit. So let's start. So we will start with over here plus minus, and then we have this, we have this, we have this, or you can, yeah. Then we have this. Right, and this is your amplifier here. This is the input resistance, this is the output resistance, this is the load resistance, this is AV naught VI, where VI is here, this is the signal resistance, and this is the V signal. Okay, so let's look at all the values. Now we have an input resistance of 100 kilo ohms, so this is our 100 kilo ohms. Then we have an open loop voltage gain of 100, so this is 100. We have an output resistance of 100, this is 100 ohms, and it is connected between a 20 kilo ohms signal resistance. So we have a 20 kilo ohms signal resistance, and then we have a 2 kilo ohms load resistance. So the first thing that we need to do is to find out the overall voltage gain. Again, we can just simply use this equation that we derived earlier over here, right? So we already have a value of Rn, R signal, RL, R naught, and AV naught. So we can just put down the values in this equation and find out the answer. Okay, so again, our overall voltage gain is equals to input resistance plus signal resistance, AV naught, and then we have this RL over RL plus R naught, right? So you can easily put down this value. Rn is 100 over 100 plus signal 20k, AV naught is 100, and then you have load is 2 divided by load is 2. R naught is okay, R naught is 100, which is going to be 0.14 kilo ohms, right? So again, make sure that you will take into account all of these kilo, millis, all of these value, right? Over here we had 100k, 100k and 100k, so that is why all of these k can be cancelled out. We have a 2k, and then we have 100 ohms. So that is why since I was writing everything in the kilos, so I ended up converting this 100 to a 0.1, right? So this is 0.1k. Okay, so when you're going to solve this out, you will get the total value of 79.4 volts per volt. So this is the overall voltage gain of this amplifier circuit. So the second thing is, now let's find out the current gain, right? So the current gain is the ratio of the load current to the current drawn from the signal source, right? So this is our II, right, and this is our I naught, and this is our V naught. So we can easily see that our I naught over here is equals to V naught over RL, right? And now if I will use a voltage divider over here, VI equals okay, so VI equals V signal into Rn over Rn plus R signal. Now if I have to find II, so I will be equals to V signal over Rn, right? So I can VI over Rn, right? So this current is going over here, so the current II will be VI over Rn, the current that is going into the amplifier. So if I will put this over here, so the value of the I that I got will be equal to V signal over Rn into Rn plus R signal into Rn. So Rn will be cancelled out, and the value I got is V sig over Rn plus R sig. Okay, so this is the value of II. So now I have to find out the voltage gain, or sorry, the current gain. And so the current gain is I naught over II. So I naught was equals to V naught over RL multiplied by II. So II will be Rn plus R signal over V signal. Over here I can rearrange this equation as this: R input plus signal over RL. Right, okay, so you know that V naught over V sig, right? So it's the output to the input that is being fed to the entire amplifier circuit is what we call as a overall voltage gain. So this is GV Rn plus R signal over load resistance. So if you will put down these values over here, so what is the value of the GV? 79.4 into the value of the input resistance, 100k plus signal resistance, 20k divided by load resistance, 2k, right? So the value that I'm going to get is 4762 amperes per amperes, right? So always consider the units. Okay, so this is the value of the current gain that we got. Again, it was a very simple problem. To start with, it was a basic amplifier configuration, or how you can make an equivalent circuit of an amplifier and then connect a load resistance and an input source signal. And we drive this initially in the last lecture. We drive this equation of the overall voltage gain. So all we did over here is to put down these values here. The new thing that we did in this example is we find out the value of the current gain. The current gain was the output load current to the input current that is going into the amplifier, right? And so the output current was very simple, V naught over RL. So we ended up finding the value of the input current, VI over Rn, and then we just divided that. So after dividing these two simple expressions, we can easily calculate the final value here. Okay. Now we will do another example of common source amplifier. All right, so we have a common source amplifier. Okay, so before I do this example, I can show you again. This was a common source amplifier that we discussed earlier in the last lecture, right? And while analyzing the circuit, we said that the input resistance to this amplifier was infinity because the gate current was equal to 0, right? So the input resistance was infinity. And then we said that our output resistance was equals to RD. So these are the values that we determined in our last lecture. Now what we are going to do, we are going to use the similar values here. So the important thing over here is that since our input resistance was infinite, there will be no loading effect. There will be no signal drop. And when that will be true, if our if our Rin will be infinite, right, then our V signal becomes equals to Vi, and the voltage gain of an amplifier will becomes equal to the overall voltage gain of the circuit. So with these basic things revised, now let's do this problem. So we have a common source amplifier that utilizes a MOSFET. We have a mu and Cox value, W over L value. It is biased at 320 microamperes, and the value of the RD is 10 kilo ohms. We need to find what is the overall voltage gain, and then we have to do the second part. Okay, so let's start with the first part. Okay. So let's start first with finding the value of the Rn. We know that in a common source configuration, since our gate current equals 0, our Rn will be equals to infinity. Okay, so the second thing that we need to find out is we need to find out the open loop voltage gain, AV naught, right? So I can go back, check the AV naught. AV naught equals minus GM into RD. So I need to find out this value, minus GM into RD. So I already know the value of the, this is the load resistance RL. This is the value of the RD, 10 kilo. And interestingly, they're both the same. Okay. So I already know the value of the RD. I need to find out the value of the GM. Okay. So I know that the value of the GM is KNVOV. All right. So interestingly, the first thing that I need to do is to find out the value of the VOV. Since again, we are using this transistor MOSFET as an amplifier, so I can use a drain current equation for the saturation region. So in order to, okay, let's call this one. Okay, so for saturation, it will be half Kn VOV whole square. So it is half mu n Cox W over L VOV whole square. So I know the value of ID, which is 320 microamperes. Half mu n Cox is 400 microns into W over L, which is 10, into VOV whole square. So if once you calculate the value of the VOV, the value of the VOV will come out to be 0.4 volts. Okay. Okay, so this is the value of the overdrive voltage that comes out. Now the second thing that you need to do is to find out the value of the GM. So GM was equals to KNVOV that we studied earlier. So what is the value of the Kn? Again, Kn is 400 microns into W over L into VOV is 0.4. So we have okay, so 10 to the minus 1. All right, so 4 into 4, 16. And then we have 10 to the 2, 3, and minus 1, 10 to the minus 2. Okay, so I can also write it as 1.6 milliamperes per volts, right? So it will be 1.6 into 10 to the minus 3. Okay. Oh, no, actually, yeah, sorry. I think... so it was equals to 4 into 10 to the minus 4 because it was microns, 10 to the minus 6, into 10 into 4 into 10 to the minus 1. So we ended up getting 4 and 4, 16 into, okay, so this will be cancelled out, 10 to the minus 4, and this will give you 1.6 milliamperes into 10 to the minus 3 milliamperes per volts. Okay, so our value of the GM that we ended up finding out is 1.6 milliamperes per volt. All right, so we can now use this value to find out the open loop voltage gain, right? So I can put down this value, put in equation 1, put in 1. Now AV naught is equals to minus GM into RD, so minus 1.6 milliampere per volt into RD. RD is 10 kilo ohms. 10 kilo ohms, so milli K. So it will come out to be okay, sorry, let me okay, so it comes out to be 16, minus 16 volts per volts. So this is the open loop voltage gain that we ended up calculating. All right, so the second thing that we need to do is to find out the value of the R naught. So we know that again, going back to the common source amplifier configuration here, we know that the value of the R naught equals RD. So I'm going to use the same thing. The third value over here that we need to find out, R naught equals RD. What is the value of RD? 10 kilo ohms. So this is 10 kilo ohms. So we ended up finding out this value as well. So the third thing that we need to find out, if the load resistance of 10 kilo ohms is connected now to the output, what overall voltage gain is realized? Now we need to find out the overall voltage gain. again going back over here, the value of the overall voltage gain will be equals to the voltage gain of the amplifier, because our input resistance is infinite and there is no loading effect. So I can use that. This is also equal to GV, so minus GM RD in parallel with RL. So GV equals AV minus GM RD in parallel with RL, and or what is the value of AV? We can also see that the value of the AV equals AV naught RL over RL plus R naught. AV naught RL over RL plus R naught. So AV naught is minus 16, load resistance is 10K plus R naught equals RD is also equals to 10K. So the value that we will get will be so minus 16, 10 over 20, minus 8 volts per volts. So this means that our voltage gain, overall voltage gain, is 8 times higher. So it is multiplying or amplifying the signal 8 times. Okay, now let's do the third quick part of this question, which is if we have a 0.2 peak sine wave signal is required at the output, right? So if we want our output signal to have a maximum peak voltage of 0.2 volts, what must be the peak amplitude of the signal, V sig? We know that V sig over V naught, V naught over V sig is the overall voltage gain, and the overall voltage gain is minus 8. So considering this minus is just a 180 degree out of phase, so it should be 8. 8 times amplification if I have to find the modulus value. Okay, so what is the value of the V sig that will give a 0.2 volts peak sine wave? So V sig will go over here and that will come over there. So our V naught over 8, 0.2 over 8, it will come out to be 25 millivolts. So this is the value of the voltage at the signal. This is the peak signal voltage that can produce a peak signal output voltage of a 0.2, and that output will be inverted because of this minus sign. Okay, so my recommendation whenever you will do any problems related to any of these specific configurations of the amplifier, always go back to the basic understanding or the basic derivations that we did. For example, over here it was a common source amplifier, and you will be able to solve most of these problems very easily, right? So most of the basic concepts are discussed there, and most of the equations are provided there. So using the same equation and the same concept, you can solve almost all of these equations and the problems. Okay, let's do one more configuration examples before we wrap up. Okay, now we have a common gate amplifier. Okay, so let's just first very quickly look at the common gate amplifier, right? So this was a common gate amplifier that we did in the last lecture as well. In which we when we connected the drain terminal to our other equivalent circuit models, right? So over here we ended up using this circuit model for the common gate configuration. Okay, so for the common gate configuration, we know that our input resistance is equals to 1 over GM here. Our output resistance is still equals to RD. Here is our overall voltage gain, and our open loop voltage gain is over here. Okay, so let's find out the values. Here. Okay, so we have now a common gate amplifier, an NMOS transistor, which has a GM value of this 2 milliamperes per volt, a drain resistance, a load resistance. Amplifier is driven by a voltage source having a 750 ohms resistance. So this is our R sig value. Right, so this value is our R sig. What is the input resistance of the amplifier? So the first thing that we need to find out is what is the input resistance of the amplifier. Then we need to find out the overall voltage gain, and then we will move to the third part. Okay, so the first thing, So the first thing is, what is the input resistance of an amplifier? Going back, the input resistance of this configuration is equals to 1 over GM. Okay, right, so Rn equals 1 over GM. So we know that GM is 1 over 2 milliamperes per volt. So the resistance, so it is going to come out to be 1 over 2.5 kilo ohms. So this is the value of the input resistance. Okay, so the second thing we need to do is to find out what is the value of the overall voltage gain. Second thing is we need to find overall voltage gain. Again, going back, overall voltage gain is this, right? With a load resistor, we have an RD in parallel with RL over R sig plus 1 over GM. Okay, so if you will put down this value, you can calculate that very easily. Let me do that over here. So GV, using this equation, RD GV equals RD in parallel with RL over R sig plus 1 over GM, R signal plus 1 over GM. So you have a value of GM. What is the value of RD? RD value is 5 kilo ohms. What is the value of RL? The load resistance is okay, no, sorry, yes, oh, both are the same actually. 5 kilo ohms is the load resistance and RD is also 5 kilo ohms. Okay, so putting down these two values, and then our R signal value is equals to 750 ohms, 0.75 kilo ohms, just to keep all the units the same. So if you're, and then we have a value of the GM, which is equals to 2 milliamperes per volts. So if you're going to put down all of these values over here, you can easily calculate the voltage gain, which will come out to be 2 volts per volts, right? So it is giving you an amplification factor of 2. Okay, so let's find out the third part of this question, which is by what factor must the bias current ID of the MOSFET be changed so Rn matches R signal. So what we are interested in is finding out the change in the value of the DID, drain current, that will that is required so that the input resistance of an amplifier matches the signal resistance, right? So this means that our new Rn, let me just write, our new value of the Rn should match the old value of the R signal. Our R signal value is going to remain the same because the source is the same, right? So it should be equals to 0.75 kilo ohms. Okay. So in order to have this value now, what needs to be done, right? So this means that now I'm going to have a new value of GM as well. Rn is equals to 1 over GM. So the new value of the GM represented over here in blue would be equals to 1 over new value of Rn. Right, so this will be 1 over 0.75k. So the new value of the GM is going to come out to be 1.33 milliamperes per volts. Okay, now we know that now what we are interested in is finding out the change in the ID that is required to satisfy this condition or to match this condition. Okay, so we know that again from one of the earlier lectures. If I will go back to show you the equation, right over here, when we were calculating these values, we also ended up finding out this equation, right? So this Kn dash W over L is just KL. So GM is essentially 2 Kn ID, right? Okay. So GM equals 2 Kn ID square root. So what we have is initially our GM value was 2 and our new GM value is 1.3, right? So how much is the factor? So 1.33 divided by 2 is 0.67. So in order to have a change of GM by 0.67, how much change of the ID is needed, right? In order to produce a GM change of 0.67, how much change in the ID is needed, right? So the change in the ID that we need to find out will be the square root of, but keeping, since our Kn will remain the same, so the factor 2 Kn will remain the same. So the change in the current will be equals to 0.67 square, which will come out to be 0.45. So this is a change in the current that is needed in order to get the change of the of 0.67, right? So so important thing, it is not, the question is not asking you over here what will be the new value of the drain current will be, or what will be the new value of the GM will be. The question is asking you by what factor the value of the drain current will change, right? So it is giving you a factor, more like a differential. So by what factor the current will be changed to get a change of the GM, or the, in order to match this resistance. When we match this resistance, our GM value, we get a new GM value. So the change in the GM value was by this factor 0.67. In order to produce this factor change in the GM, we need to change the drain current by a factor of 0.45. Okay. So with that, this was our final example that I wanted to do. I will also upload some more example problems, or kind of recommended exercise problems for you to solve, and possibly their solutions later as well. I would encourage you to do those problems. So with that, this was our final lecture on the MOSFETs. We are finishing up our MOSFETs contents now, and starting next week, we will move to our next topic, which is bipolar junction transistors. All right, thank you so much, and have a good day. Bye-bye.